There are three main exceptions to the octet rule. The first is where there is an odd number of electrons in the molecule. The second is where there are fewer electrons than would be in the corresponding group 8 element. And thirdly, where there are more electrons than would be in the corresponding group 8 element. Let's see some examples of these exceptions. The first we'll consider is where there are an odd number of electrons. We'll look here at nitric oxide. If you look at nitric oxide, you can see it's made up from nitrogen and oxygen. Nitrogen has 5 valence electrons, oxygen has 6 valence electrons. And when we bring them together to form nitric oxide, we have a total of 11 electrons to play with, an odd number of electrons. Let's see where those electrons go to form bonds. Well, we use 4 of them to create a double bond. A single bond is 2, a double bond is 4 electrons. We depict a double bond as 2 parallel lines. Next, we can see that there are 3 lone pairs, 3 groups of 2 electrons that aren't forming a bond. That's why we call them lone pairs. Lastly, and this is the, if you will, troublesome electron, there's one more electron, and that's what is making the molecule have an odd number of electrons. This is described as a radical. Nitric oxide is very reactive because of this radical. The second case where the octet rule breaks down is when we look at atoms that have too few electrons in the outer shell, so that even if they are paired up with other electrons from other atoms in making covalent bonds, we still don't have the 8 electrons necessary to have stability and to meet the octet rule. We see this commonly in group 3 elements such as boron and aluminium. Group 3 elements have 3 valence electrons. So if we were to pair each of those electrons up with another electron coming from another atom by creating a covalent bond, we would still only have a total of 6 electrons in the outer shell, not the required 8 for stability. We see this in the example of hydrogen and boron creating bonds of a covalent nature. 3 hydrogens bonding with 1 boron. We'll see the 3 electrons in the boron outer shell being paired with 1 electron in each of the 3 hydrogen atoms to create a total of 6 electrons in the boron outer shell. We know to meet the octet rule that we need 8, and this results in a very reactive molecule. We draw an empty p orbital to depict the opportunity other molecules containing electrons would have to add further electrons to the boron and thereby achieve the 8 electrons necessary for stability. The best chance the octet rule is going to work is where the second shell is partially filled. When that gets completely filled up, and it's the third shell that's partially filled, especially when it's the 3 p orbitals that are partially filled, we observe a new phenomena. And that allows for extra electrons beyond the 8 of the octet rule to be stored, and yet the molecule and atom are still stable. Great examples of this are with the atom silicon, phosphorus, and sulphur. If we look at silicon, we'll find there are 14 electrons, 4 of which are valence electrons. Now that means that if we add an extra 4 electrons, we will meet the octet rule and gain stability. With phosphorus, we have 15 electrons, which are 5 valence electrons, so another 3 electrons will allow the octet rule to be met. And finally, sulfur has 16 electrons, of which 6 are valence electrons, so it's another 2 electrons that we seek to gain octet rule stability. Now, all 3 of these examples can be stable with 8 valence electrons, and yet importantly, also they are stable with 10 valence electrons and even 12 valence electrons. This is because in energy a little higher up from p orbitals, we find the 3d orbital, and this allows for extra storage for those extra electrons. When this happens, we describe the molecules as being hypervalent. Let's consider some hypervalent molecular examples of this. First, we're going to look at a silicon molecule. It's drawn as a Kekulé structure. So what we want to do is add up the number of lines attached to the silicon atom. Each line represents a single bond, and that single bond is made up of 2 shared electrons. So we notice there are 5 single bonds, and thus we have 10 valence electrons. And yet the molecule is still stable. Another example is phosphorus. Here we're looking at triphenylphosphine, which is commonly used in a Wittig reaction that we will also talk about. But here we're using it to demonstrate hypervalent molecules. So let's look at the phosphorus. You'll see here there's a double bond. That's where we have 2 lines joining the same 2 atoms. A double bond contains 4 electrons. So let's add up the number of electrons associated with this phosphorus atom. We'll see that yet again there are 10 valence electrons and the molecule is stable. Lastly, let's look at the sulfur atom. The sulfur atom in this example shows a double bond to an oxygen, which, as we've talked about before, involves 4 electrons. We have a lone pair, which are the 2 dots next to each other, and that is 2 electrons that aren't bonded to anything. And then finally the 2 single bonds. So if we add all the valence electrons up, we will find again it's 10 electrons and still stable. This is called dimethyl sulfoxide and is commonly used as a solvent in organic reactions. By modifying the dimethyl sulfoxide very slightly, we arrive at dimethyl sulfone. This involves changing the lone pair, those 2 dots next to each other, for a double bond to an oxygen. Now the lone pair was 2 electrons. A double bond to an oxygen is 4 electrons. So again, let's add it all up. Number of valence electrons here is 12 valence electrons, and the molecule is still stable. Silicon, phosphorus, and sulfur are not the only atoms that have these properties. We find them in a number of other atoms, and these include chlorine and iodine.